and be fresh. And today I'm going to be presenting problem number 2, droplet microscope. And this is our outline for the report. Problem statement. By looking through a single water droplet placed on a glass surface, one can observe that the droplet acts as an imaging system. Investigate the magnification and resolution of such a lens. And our main focuses are, first, the relation between the radius of droplets and the magnification. And second, relation between the radius of droplets and the focal length. And this is our experiment setup. We use micropipette, iPad, iPhone, magnifier, and ruler. And in case you're wondering, the little gridded box in the droplets are pixels on iPads. Okay, now let's talk about our theory. First, let's define the droplet shape. So we use the Laplace pressure equation to get us theoretical A1 and B1, and A1 stands for the radius of the droplets, and B1 stands for the height of the droplets. And from getting the A1 and B1, we can then use the elliptic equation to get a formula for this elliptic shape. And therefore we can also use the A1 and B1 and use the radius of curvature calculating methods to get the radius of curvature of this point. And now let's talk about the focal length defined. And this is the lens maker's equation for state lenses that we are going to be using. Okay, so R stands for the radius of curvature. And since one side, which will be R2, is this side, the bottom side, since it's flat, the radius of curvature of it is nearly infinite. And also the water's refraction rate is 1.333. And therefore, we can shorten the equation down to 1 over the focal length is approximately equal to 1 over 3 times the radius of the curvature for the ocular lens. Okay, so now let's define magnification. So we use the image distance and the object distance of two screens. One is the upper part and the lower part. So since we consider the bottom part of the droplet and iPad screen as one screen, and since it's flat, and also the light rays through the iPad will be fixed, therefore we can neglect this part of the focal length and only focus on the upper part. So therefore we can get the magnification is equal to something like this. Okay, so now we're going to be talking about resolution. We use numerical aperture to define our resolution, and this is the equation for the numerical aperture. And N is for the rotor refraction rate, which is 1.03, and the sin theta we are going to be using the focal length and A1 to get the sin theta. Okay, so first let's talk about our first experiment. In our first experiment, we focus on the volume and shape of the droplets. So we measure A1, the radius of the droplets, and B1, the height of droplets, to define the elliptic shape of the droplets. And this is a rough overview of our droplets. And as you can see, as the volume increases, it tends to be more an elliptic shape, and at lower volumes, it resembles a more sphere shape. And these are the results. And as you can see, it has a convergence for the radius of the droplets and also the height. And also, as you can see, the units here is slightly different, and A1 is larger than B1, and therefore we can assume that when the volume is increasing, the radius of droplets is what the volume is affecting the most, because B1 doesn't change as much as A1, as you can see in this graph. And from the experiment, we can know that as the volume increases, the radius of the curvature changes, and therefore the shape would not always be the same. And second experiment, we focus on the magnification and focal length calculating. So we measure the amount of pixels in the middle of the droplets using the magnification formula and the focal length calculating methods we talked about earlier in the theory. We can calculate them. And this is the trend of the focal length and the magnification for our experiment results. And as we can see, as microliter increases, the focal length also increases. And for the sunlength magnification, you can see that at lower volumes it has higher magnification, and as volume increases, the magnification drops down and eventually comes to a convergence. Okay, so now let's talk about our theory with our experiment results. So first, let's take a look at our blue line, which is the ellipse mode of elliptic shape at first. So therefore, we first drew the blue line. And compared to our magnification first, we can see at the higher volumes of water, the blue line, which is the ellipse model, is more applicable to our experiment data. And then for the focal length, it's also the same. So we wonder why it doesn't fit our experiment results at lower volumes. And therefore, and for this, we come up with a sphere model because we observed that at lower volumes of water droplets, we observe an inwards curve down below on the lower part of the droplet. It curves inward. So therefore, we assume that it resembles a more sphere shape at lower volumes, and therefore we use a sphere model, and as we can see, it applies more to our experiment results. And from the diagram on the previous page, we can see the minimum focal length value is around 4.9, and for the maximum focal length, which is the convergence line, is around 8.45. And for the maximum magnification, which observed in our experiment, is 2.6. And for the minimum magnification value, which is close to 1.5. And now let's talk about numerical aperture. We observed that at higher volumes of water droplets, the numerical aperture is higher, therefore meaning a better resolution is formed. And this is also, the blue line represents our ellipse model, and as you can see, it applies more to our experiment data at higher volumes. And the red line represented the sphere model is more applicable to our experiment data at lower volumes. And for our conclusion, from using the Laplace pressure equation and elliptic shape equation, we can define the shape of the droplets and therefore getting us theoretical values of A1, B1, focal length, magnification, and the radius of the curvatures. And second, through experiment 2, we observed that below around 20 microliters, it's more applicable to sphere model. When it's about around 20 microliters, it's more applicable to ellipse model. Okay, and last but not least, there were experiment first 1 and 2. We observed that numerical aperture increases as the volume increases, eventually reaching a balance at high volume. And that's it for our presentation. Thank you.
So it's time to check opponent question.
So I have a couple of questions I want to ask you. The first question would be, did you make sure that the shape of the droplet you drop for each time is the same?
Okay, so for this
question, just
yes.
Okay. And what about the glass like you put on the iPad, right?
Yes.
The iPad is horizontal.
Yes, it is.
Okay. And what about your phone? I saw you have a camera on the iPad, right? And you take a picture of it. So what about the camera, the place of the camera?
Yeah,
is it in the same place?
Yes, it is.
Okay, it's in the same place. So do you think the environment will affect your experiments?
It doesn't.
Humidity or temperature?
It doesn't will, and it will affect the evaporation rate and so on. But in this experiment, we
possibly to control this, right?
Yes, we did.
Okay, thank you. And did you think that the one which will affect the magnification would be the focal length?
Pardon?
I say, do you think which factor will affect the magnification most? Focal length or curvature radius?
They both will affect.
It both will
Yeah,
affect.
because
Okay, sure.
affects.
And what about the resolution?
Resolution, it's because the model of the droplets.
Okay. So do you think the magnification will have a limit?
It does have a limit because, as we can see, at higher volumes, it decreases and finds the convergence line.
Okay, thank you. And in your experiment,
Yes.
when you found the resolution, did you use your eye or camera to observe it?
Yes, we did. We used both our eyes and camera to capture the picture and also observe it.
Both in the same time?
Not really, but like in a short period of time.
Okay, sure. And did you find that it would have an aberration in your experiment?
Pardon?
Aberration.
You mean the distortion?
Yes.
Yes, we did, but that's not our focus of our experiments.
Okay, thank you.
Thank you. So, hi.
statement, by looking for a single water droplet placed on a glass surface, one can observe the droplet as an imaging system, investigate the magnification and resolution of such event. And in my main focus, I will talk about why the droplet can be seen as an imaging system and how do the relevant parameters affect the results. So, to overview the report, in his theoretical model, he talked about the place emission and the electric depression and numerical everything, and lens maker's depression. And his goal here will be a clear explanation of his theoretical model and demonstrate as the model. But his goal here will be only suitable for specific condition that he only use a single impression to describe the droplet, and only in ideal situation, and doesn't consider enough factor to establish the model. If one have some error, I will correct in the discussion. So, in experiment and setup, he do a different volume of the water, different curvature radius of droplet, and different diameter of the droplet to see its magnification and resolution. And his goal here will be consider variable well and consider droplet is thickness or thickness, which I will discuss it later also. And he doesn't consider enough variable and like a parameter, and he will might have some error in his experiments. And his data analysis, he talk about microliter and the focal length and side length and magnification and resolution. And his goal here will have a comparison. He doesn't have the comparison and theoretical and experimental value. And Phil with us, and he doesn't have a theoretical model. So I will talk about is teaching how to do a theoretical line. And next, this is a discussion point. And in here, I will talk about the definitions of imaging system like signal or signal, and how does he see the definition of it, and the accuracy and consistency of the theory reporter mentioned. Like he talked about the lens maker's impression, and I will talk in discussion with him is the lens maker impression fits in his experiments. And the condition environments of the experiment are such as, like I said, the humidity or temperature will also affect it. I think it should be considered. And the relevant parameter in the experiments. And the results of different parameters, like you talk about the curvature radius, focal length, diameter, and the comparison of different results. And the spherical line is because it doesn't have a spherical line. So we can see in the spherical model it fits results. And that's all my presentation. So I want to describe with some this group. So I heard you say you use a formula to calculate magnification.
Yes.
And what is the formula you say? Is it Gaussian loss?
This one?
Or you use this one?
Yes.
Okay. So is this one suitable for the thickness?
Yes, it is.
Okay. So in your job is the thickness.
Yes.
And how did you prove it is the thickness?
Okay, now may I use the blackboard?
Yes.
So we originally are like trying to think of theory out of this.
Yes.
Okay. So we first look at smaller volume water, and we observe that at lower volume there's going to be an inverse curve.
So you think
Yes.
we have this as called a thickness? Is
Yeah,
the
because-
definition of it?
Because like we consider this to be the middle length of it, and we consider about the lower one. That's the reason.
Okay, but what if the job is like this? We call it a thickness. We also have the curve here.
Yes, but like it's like not obvious. So in our
Yes.
in our one we
And
have
that's a
to
problem in here because I want you to do an experiment and prove this. Like you need to do an experiment. If you find out that some magnification is not fit with your theoretical model, and that's not will be like you use a thing that theoretical model to fit with your experiment result, and you found out that that's not fit with, and you can know that this is something. So you need to do an experiment.
Okay, so when we are conducting experiments, we did find out like as the volume increases, the inverse curve becomes less obvious. Is that correct?
Okay. Yes.
So that's the reason why at larger volumes that the left model fits better than the sphere model, and because we consider it to be a thick lens and the inverse curve is always there, but it's just not obvious. So therefore, we think like that's the reason why we choose the thick lens for version.
So since that we have different opinion, but let's move
Okay.
on to another. I want to talk about the theoretical model you have, like lens maker. Can you return to the lens maker's page?
This one?
Yes.
Okay.
I heard that you use an iPad to see, right?
Yes.
iPad will have a screen, right?
Yes.
And what is the material of the screen?
It's just basically like
Glass.
it's not like entirely glass, but in the problem statement, it only
Yeah.
talks about glass. And we also conduct the experiments on glass, and we found out like because we are observing the pixels in the middle, right? So therefore, the only difference between the iPad glass and the glass and how the droplet shape will form is, may I use the backboard again?
Yes.
Sure.
So This is an iPad,
Okay.
and we observe that it will have a more obvious curve now.
Yes.
And when we are conducting experiments on normal glass, we would observe that it's going to be something like this.
Oh.
And since we
It's
only,
hydrophilosophy and hydrophilosophy.
especially like the viscosity of the water, so
Okay.
that's and so we only focus on the middle part, so therefore
Sure.
we won't.
I know. But I have a question on that. Since you use the lens and first impression, and you explain that the N1 here, which is a reflection of water, right?
Yes, it
But
is.
what about the screen?
You need a screen because
Yes, the screen has its own refraction, and you didn't consider it.
but like when we are
And you didn't modify it.
okay.
Tell me how to modify it.
Okay, so when we are observing the pixels, we observe the middle light. So we assume that the lights come from straight from the screen up. So
You're really sure about this?
yeah, because like we only observe this. So I mean there might be errors, but it's like slightly accuracy.
Okay, so you're saying that glass won't affect it.
Yeah, it won't affect as much, but like in our experiment we neglect
If
it.
you turn to the page, you have a data. Yes, look at your data.
This one?
This one, you didn't have error bar.
Oh yeah, that's a
Yes.
mistake.
So
But
if you have error bar here, you may know that's because of level of factor.
okay, may I?
Okay.
So we actually did make a graph with the error bar, but when we're doing it, like even though we have error bar, most of the data that we get in the experiments are still fitting with the serial model. So that's the reason, like
Okay, so since you say the magnification have a limit,
yes.
you understand why?
Okay, so okay, this is it. So we all know that as I explained earlier, we use focal length to calculate magnification. That's
Yes.
correct. Okay, so as you can see here, the focal length increases, but as volume increases, it would have a convergence line. Okay, so when we're using the focal length to calculate the magnification, focal length is affecting the magnification value. That's right.
Yes.
Okay, so when it has a convergence lens, it will also make the magnification to also happen. So that's, I think, the explanation for that question.
Okay, thank you. So I have a question I want to ask you. You say that you put a camera in the same place, right?
Yes.
And did you consider that the camera will also have a focal length itself?
No, we did not. But like,
You didn't consider it. And it will affect the magnification a lot because when the camera has its own focal length, it will affect it. You put it in different way, the magnification will change.
okay, so I want
So
to
you didn't do
clarify.
an investigation in here?
I want to clarify one thing, but like, I think I kind of misunderstood the problem. Are you talking about like when we are observing the droplet from side or above?
No, I mean the camera have its own focal length. Just like when you use a camera to see the resolution, right?
Could you use Blackboard to demonstrate that? Because I don't think I followed.
Like, look at this. Here will be your camera, right? And here will be a dropping point.
Yes,
And
it
here
is.
is the iPad, right?
Okay.
But camera itself will have its own resolution and focal length.
Yes, I
So
agree.
it will affect it. If you consider it in your experiment.
But like, I think for the magnification, we use the serial data and also the experiment results, but they fit. So I think for your question here, I think the focal length of the camera isn't like really affecting if we are put it in the right position. So therefore, it won't affect the resolution and magnification that much.
Okay, so I will have a question I want to ask you. I want to know more about it's like in your opinion. Do you see the curvature radius affect the result? You said curvature radius and focal length will affect the result, right?
Yes, right.
But in my opinion, I think that when you say the curvature radius affect the result, actually curvature radius is affect the focal length.
Yes.
And the one which is really affect the magnification is focal length, not the curvature itself.
But like the curve we use, okay, let's turn back. Okay, so we first get out series A1 and B1, that's correct. And then we use this coupling method, the radius of curvature, right?
Yes.
Okay, so then we use this radius of curvature to calculate the focal length in the next page. Using the next matrix equation, we get the proportion of the focal length is approximately equal to 3 times the radius for r1. That's correct.
Yes.
And that's how we connect all of the.
So you connect it. So.
Yes.
And do you agree with me that the main factor to affect the magnification is focal length?
Yes, I agree.
Okay, so can you turn to the data? One is that the graph doesn't have mention the y-axis plot. Yes. Oh, okay.
This one?
Yes, this one.
Oh,
Tell me what is the y-axis
Oh,
didn't say.
this is the focal length because I thought I mentioned the microliter, so okay, that's my fault. But this is the focal length, and for this one is magnification.
Okay, so we need to mention the
Okay.
presentation.
Thank you.
So I have another question I want to ask you is that turn to page resolution one.
Resolution one.
Yes, I have a question I want to ask you. Do you really quantify the resolution?
Okay, so there are like different resolution forms, like the optical resolution and the image resolution. But for this, there are just like different ways to define the resolution. And for this experiment, we choose the optical resolution to define our resolution. So therefore, the numerical curvature is something that we choose. And from this, we can use the focal length and the radius of the droplets to calculate.
Oh, so you use another way.
Yes, like there are other ways, but you can also define it in other ways, but this is this.
Okay, so you can okay. I have another question I want to ask you is that you say that you didn't consider about aberration, right?
Pardon?
Aberration.
Okay.
You didn't consider it.
Yes.
So that's the thing that which I think is really important in the dropping, in the imaging system. Because it will affect your magnification and resolution.
But like our main focus of this experiment is in the
And then how did you calculate magnification? Because when you observe the magnification, it will affect by the aberration.
No, because we observe the aberration at the edges of the droplet, so that's why we chose the middle.
Edges of the droplet?
Wait, okay, so can you define aberration?
Okay, like, there are some different kind of the aberration. First, it will look like this. First one will look like this.
Okay, yes.
And which one in your experiment? I want to see it's because maybe we discuss about aberration and how would you figure out what aberration will affect your results.
As you can see, it's curving inwards.
Okay. So it's something like kind of like a incursion distortion. Yes, just like a left one and right.
Oh, yes, that's right.
And can you explain why this happened?
Because of the edges, like, as it gets closer to the edges and this
So
curve.
which part did you observe in your application? Can you point out? Just point out.
This one.
This part.
Yes.
So you didn't consider the age of
Yes, because that's not our main focus.
Okay, so
That's right.
that, and since we all talk about the data and theory, then that's all my discussion.
Okay, thank you.
So here is my summary of my discussion. So in the discussion, we talk about definition of stage and thickness, and he declared by his own opinion about the definition of it. And magnification and resolution happen by the glass. And we talk about lens maker Patrick impression, which I think he had an error in it because the glass will have its own reflection, and he didn't consider it, so he need to improve it in the future. And then we talk about the focal length and curvature radius, and I think he agrees with my opinion is that focal length will affect the magnification more. And he also talked about aberration, which he doesn't consider in his experiment. So I think the next time when you do the experiment, you need to consider it's not just because you can't just to see the middle part of it, because aberration you can know more about the droplet this kind of imaging system from the aberration and to investigate it. And that's all my opinion and suggestion. Thank you.
So, it's time to review the questions to resolve
Okay, so first question to the opponent. What do you think is the definition of resolution?
I think the definition of a resolution is like where you have the minimum angular resolution.
So it's minimum
two
angular
lines,
resolution.
yes, and 2 lines, and you can define it.
Differentiate between 2 points?
Yes.
You can go okay. What do you think is the definition of resolution?
Okay, so it's basically from the understanding and why we use the numerical curvature is because when we are so how do you the distance between
Wait, so
like,
you
how
use
do you
numerical aperture to measure resolution. So what does numerical aperture measure have to do with resolution?
Okay, so it's basically when two objects and how you connect, like the distance between them and how you distinguish them. And numerical
Do you
curvature,
think numerical aperture determines the distance?
yeah, it's like one of the factors in calculating that. So that's why we chose numerical curvature.
Okay. Could you go to your elliptical assumption from your Laplace pressure equation?
Pardon?
Could you go to the part where you use the elliptical model for the
Is this one or?
Yeah. How do you go from the Laplace pressure equation to the elliptical equation? Like, how does it do it?
Okay, so first we use the Laplace pressure equation to calculate the theoretical A1 and B1, and you know A1
Oh, okay.
and then we use the A1 and B1 to calculate.
Could we go on to the lesson equation slide 8?
Pardon?
Could you go to slide 8 of
Slide 8. Okay, slide 8.
equation? Right. How do you get R from A and B?
Pardon?
How do you get R1 from A and B? Is R1 just B1 or do you have
No, R1 is the radius of curvature of the arcs, and we use this one, the A1 and B1 to
A
calculate.
squared over B. Oh, okay.
Yes, it's like all connected. So
Okay. Then this question is for both the opponent and the reporter. Do you believe that the screen is part of the lens? Do you believe the screen is part of the lens?
I think it's, so you need to consider your density coefficient.
Yeah.
Density coefficient can fit with this.
yeah, and,
Because, it doesn't have a recurrent of this.
and for my opinion, I would consider the screen and the common side of the lens to be the same side of the screen. So that's we consider it as one screen.
Okay, so this is a follow-up to it. What are the parts of this imaging system that Tom described? Since the Tom described the droplet on a glass surface, right?
Yes.
So what are the components of this imaging system? Like describe it in terms of the models used for each of them and like how the parts are.
You mean the like models for
Yeah, so like what lenses, what prisms, and like what aperture stops are there?
the stick lens,
Okay.
and for then for model we use elliptic model for higher volumes, and at lower volumes we use sphere model.
Okay, so you use a sphere model for a lens. Okay. Do you think there are anything besides the droplet as a lens?
Drop the excellence. You want me to make an example of this?
So since it's an imaging system, right? So it's not just one component. What are the other components?
Probably have,
Okay.
Hello, my name is Ethan, and I'll be reviewing problem number 2 droplet microscope. So the problem states that by looking through a single water droplet using a glass surface, one can observe that the droplet acts as an imaging system. And we have to investigate the magnification and resolution of the lens. And then the report's main focuses were the relation between the radius of the droplet and its magnification, and the relation between the radius of the droplet and the focal distance. So for the report's performance, first, for the phenomenon, they investigated it by looking at the droplet on a device image, such as an iPad or iPhone, and looking at the grid of lights to look at the magnification and the resolution. For the theory, they used Laplace pressure to figure out what the elliptical shape is, then use the lens maker equation from the radius of curvature they got of the droplet to get what the magnification equation was. For the experiment, they compared the radius to height to figure out how volume affects both of them, and they also measured the focal length of the magnification. They also measured the numerical aperture of each water droplet. In regards to probes, they had a good phenomenon demonstration that had really clear photos that showed what they were measuring. They attempted to control radius of curvature using the volume. They discussed the numerical aperture, and they had good qualitative data analysis by looking at the trends in their graph. However, they didn't count the index of refraction of the foam glass. They did not analyze resolution affecting factors besides the numerical aperture. So for the aberrations that the mentioned, and they also did ignore the last one. For summary of the opponent's performance, they summarized the limits of the droplet formation theory. They brought up limits in controlling the experiment, and they brought up ways to improve the data analysis. In regards to the approach, they questioned the theory limits in regards to the intersection between the spherical model and the elliptical model, and they also mentioned thickness and length as an important factor for both the droplet and for the glass. However, for glass, they did not explain why all of the points they brought up were important, and they did not clarify aberration besides the data. So for the first discussion, they discussed was if the droplet was a thick lens. The opponent said that you need to prove that the droplet is a thick lens, and they recommend trying the thin lens equation to showcase that the thin lens equation doesn't work. The reporter said that because they tested the thick lens using the curve matches up, they didn't test the thin lens equation. I agree with the opponent that using a thin lens equation will help clarify this. However, I feel that, that since the thick lens equation matches the theory, there's no need to test the thin lens equation because the thin lens equation is just an approximation of the thick lens equation. Okay, next one. The second discussion was the diffraction index of the screen a part of the lens. The opponent says that the diffraction of the screen is part of the lens and should be included in the lens equation, and that the opponent says the glass will affect it. However, we believe that the glass is extremely relevant because it's an additional prism that affects longitudinal displacement of the lens without affecting the magnification. Regards to experiment, they also discussed how the focal length of the camera affects the magnification. The opponent stated that the camera has its own focal length, which will affect the results of magnification. Well, the reporter said they did not consider it because they considered it a minimal effect. We partially agree with the opponent that the magnification is very important. However, because the reporter only analyzed the trend of the data, because the magnification of the camera is just a multiplying factor, the trend will be the same. And then additionally, they discussed how the curvature affects the focal length. The opponent said the curvature affects the magnification more than the focal length, while the reporter said that the lens equation gets the focal length of the curve. We agree with the reporter because the lens equation basically just gets the focal length from the curvature, so it's not really a question of which is more important. They also discussed the resolution. Reporter said only using numerical aperture. Opponent said choose from the aberration. Opponent brought up hair distortion. They also discussed error bars. We agreed that they should add error bars. And then for points plus, we discussed we believe the effect of glass is important. That the spherical aberration should also be included.
Okay, so now thank you for opponents and reviewer, and now we're going to be concluding remarks for our. Okay, so our strengths are the application of theory and model, and second, the various methods to ensure the accuracy of the theory and experimental results match. And third, explanation of different scenarios. And for clarification, first I'll point out we use both sphere and lens model for our experiments. And for lower volume, sphere model is more applicable, and for high volume, lens model is more applicable. And also room for improvements. First, we need to consider the focal length of the camera, but I think if it's positioned at the right position, it's not going to be a major factor. And for second, experiment and analyze the image distortion, because our main focuses of our experiment this time is only about the central part of the droplets. Therefore, we didn't consider about the image distortion. And third, we need to add error bars to include the errors that we observed in the experiments. And that's it. Thanks for listening.
Okay. Thank you. It's time for the text from our jurors. I think the interface between the droplet and the lens is more important. I think the interface between droplet and the glasses is important. Your equation of the path pressure equation, I think it must be modified. But can you give as a comment on the interface effect, how to affect your observation?
You mean the interface of this part, right? Okay, so because we observed the image of pixels at the central. So we don't think that will affect much of the experiment results if we like consider the interface of the droplets, because we make sure that they're all like
Okay, for the reviewer and the opponent.
I think it will affect it. Like, I don't think that he used the question is reasonable in his experiment because he's dropping the glass and he didn't consider if the glass is like with the droplet is like hydrophilosophy or hydrophobically. So I think we should be more considerate of this.
I think that the surface integration of the surface tension between the glass and the water droplet would be really relevant to the problem, as it would help then investigate more different shapes of the water droplet. Since you've only looked at the very specific condition of the water droplet on the phone case, however, for just his specific experiments, I think since he kept the surface tension constant, there wasn't really as big of a need to investigate.
So, any other questions?
So maybe I comment a little bit on the previous question. I'm not going to comment. I mean, just would like to say, I would just would like to give you some example. So you can imagine that if you not using the glass, if you use let's say wood, then probably the droplet shape will be not as beautiful as you show. So that's the reason we think probably. Okay, I also agree with you. I mean, the interface interaction
But that's like
between the
relevant to the
droplet.
problem statement. Because in problem statement we stated that we are going to be using glass surface to investigate.
Yeah, but the question would be like, even in the glass, so they have some, I'm pretty sure they have some parameter which will tune the interface effect between the droplet and your interface, which we didn't show it in your equation. Probably it is also because for the glass, I mean, this coefficient is very small, such that it won't appear in the Laplace equation, but you need to tell us.
Okay, thank you.
Please.
I think such a volume control is very important, right? I see volume control.
Volume control, yes.
So you add maybe 2 microliter or 3 microliter
Yes.
in your glass, right? So how do you control the error for the volume?
Oh, we use a micropipette to drop
But the micropipette, it is hard to control the microliter because if you control 1 microliter, right? It has some error bar.
Can I okay, so what you're trying to say is that when we are dropping a droplet, it's hard to control the volumes. Is that correct?
Yes.
Okay, so basically we did experiments like a lot of times. So and for the drop pipette, that's what we find the most accurate one compared to other sirens and stuff. So that's I think it might cause some inaccuracy, but compared to other sirens, it's probably the most accurate one.
Okay, for review.
Are you talking about the? We agree
Volume
with.
control.
Yeah, I think that they need to add better error bars because the micropipette, when they add in different volumes of water, it's really inaccurate.
Okay, so I think that because in his equation they have a connection, one is the curvature radius, right? So I don't think that water volume, if this is really accurate, is not that important, just like he said. But I think the most important is the curvature radius. So I think if he control curvature radius, like what he wants, and it will be more important than the water volume. That's my opinion.
So I would like to know the opinion about how to control a certain tension of the experiment. Since the curvature of the droplet is influenced by the surface tension of the droplet and the surface tension of the surface. Here is you use a glass, right?
Yes.
So I would like to hear the opinion of some.
Okay,
Time's
so
up.
we
So
conduct
time's up. Is it okay for answer?
Yep, yes.
Okay, so we conduct the experiments in the same conditions in the same time, so that's how we control it. And if we conduct the experiments in an extended period of time, that might cause errors.
I think for the problem we're looking at, the main focus of it is the optical property. So the only thing that matters is the shape of the droplet, right? So I think that he could completely bypass the Laplace pressure to predict the shape of the droplet, and instead just approximate the droplet shape by measuring the diameter, the height, and maybe just curve it in a line to the edge of the water droplets.
And I think maybe he can use a washer, or maybe he can do more experiments to like and then make it have the same shape, and to take more picture about it, and to choose the accurate data he wants, not just only do the one experiment.
Okay, thank you.
Thank you.
This time, jury is going this way. Seven, 8, 7, 7, and 5. Second row for the opponent. Ratio 8, 9, 8, 9, 7.
So the monitor doesn't show.
This way.
Yes. Last for the review.
Ratio 6, 8, 5, 7, and 8.